Okay. So here's how I usually like to do things. I'm going to be talking about stuff. I'm going to check in every now and then to see if anybody has questions. If you have a question, feel free to unmute yourself and ask, or drop it in the chat, and I'll make sure to address it. And in my view, the only dumb question is the question that you have but don't ask. So this is a judgment-free zone. No one's going to think you're dumb for asking a question that you might think is obvious. Other people might have the same question, and it only helps us if we can make every topic as clear as possible. So please don't hesitate to interrupt me and ask questions. So yeah, let's get started. So acids and bases, the basics. So historically, there are three well-known classifications of acids and bases. The first one was developed. Oh, by the way, the slides will be available for anyone who wants it after this session. So don't worry about writing every single word down. So the first definition was Arrhenius acids and bases, and by that logic, acids produce H+ in solution, and bases produce OH- in solution. So you got protons and hydroxide ions. And this is a pretty narrow definition of acids and bases. It applies to a lot of well-known ones, but not all acids and bases actually have these properties. So it's the narrowest definition. Second definition was developed by Bronsted and Lowry. According to them, acids donate protons and bases accept protons. This is a better definition, since we now know that most acids actually donate a proton to water, forming hydronium ions, or H3O+, and bases actually accept a proton from water, forming hydroxide, or OH-. But we weren't quite done. Some acids don't even have protons, especially those with metal atoms. So we arrive at the Lewis definition, where acids are electron pair acceptors and bases are electron pair donors. And this still includes Bronsted, Lowry, and Arrhenius acids, but it also includes other systems like electron poor systems like BF3, for example. So with that, let's look at what makes a good acid and a good base. So a good acid is often one that has positive charge, and if not having positive charge, has a really low electron density at the acidic site. So if we look at the top two molecules, we've got AlF3 and AlCl3. So if we think about which one might be more acidic, well, we know that fluorine and chlorine are both pretty electronegative, but fluorine is more electronegative. And that means that it's going to pull on those bonded electrons more strongly than chlorine will. And that leaves the aluminum atom electron deprived. And if the more electron deprived that atom is, the more acidic it is. So AlF3 is the stronger Lewis acid. For our second example, if we look at the bottom two molecules, we know that alkyl groups donate electron density toward a positively charged site. And since the cation on the left is tertiary, it has three alkyl groups around it, it benefits more from this donation than the right cation, which is secondary. Therefore, the right cation has a more electron deficient site, which means that it's a better acid. Similarly, we're looking at Lewis bases. A good base is likely going to have a negative charge, and if not a negative charge, at least having high electron density. So with the first example, we're comparing hydroxide and chloride ions. Both ions will have a negative charge, but oxygen's electron cloud is actually much smaller than chlorine. So the density of negative charge is higher, and therefore OH- is a better base. If we're comparing acetate and ethoxide, both of them place a negative charge on an oxygen atom, but in acetate, the negative charge is actually shared between two oxygen atoms via resonance. That places a partial charge on each. In ethoxide, which is the molecule on the right, there's nowhere else for the charge to go. So the electron density at that oxygen atom is higher, and therefore ethoxide is a stronger base. Did I say that tertiary? Okay. going back to the previous slide. Okay, so the tertiary has alkyl groups which donate electron density. You got that right. But that actually makes them, that actually makes in this case a worse acid, because you want your acid to be as, that acidic site to be as electron poor as possible. And if you have more alkyl groups giving you more electron density, you're not as electron poor, which makes you a worse acid. That's the one on the left. And the one on the right doesn't have as much support electron density donation from its surrounding groups, meaning that it's more electron poor, which means that it's a better acid. Does that make sense? Okay, good. So the more substituted the molecule. In the case of, if we're looking at like carbocations with alkyl substitution, yes. Some more substitute is kind of a general statement, I would say, but I would say if you have like anything that, if you have something that contributes electron density to that acidic site, like resonance or hyperconjugation, like the substitution is doing, that's going to reduce the acidity. Okay, so this is where I have stopping point for questions. Any other questions before we keep going? Okay. All right. So let's talk about pH and pKa. So these are two pretty important concepts for the MCAT. So pH is a reflection of a system or a solution, how acidic or basic it is. It reflects the concentration of hydronium ions, or H3O+, and it's calculated as the negative log of hydrogen ion or hydronium ion concentration. A lower pH is more acidic and a higher pH is more basic. And this is pretty common knowledge for most chemistry students. pKa is a reflection of a particular acid, not a particular system necessarily. And it reflects how acidic the acid is. And so a given acid will just have one pKa value no matter what. Ka, which is also specific to each acid, is the acid dissociation equilibrium constant for a given acid, as shown here. And the higher it is, the more acidic the acid is. And since pKa is the negative logarithm of Ka, it goes the opposite. Stronger acids have lower pKa's. Okay, now let's talk about pH, pOH, and Kw, also important concepts for these calculations. So Kw is the dissociation constant for water. You might already know this, but water can actually undergo autoionization, where two water molecules interact, one acting as an acid, one acting as a base, to form a hydronium ion and a hydroxide ion. And that constant, which is the product of the concentrations of hydroxide and hydronium for a neutral solution, is 1 times 10 to the negative 14th. And based on just doing the math on that, if we look at pH versus pOH, pOH is calculated the same way that pH is calculated, where pH is the negative logarithm of hydrogen ion concentration, and pOH is the negative logarithm of hydroxide ion concentration. Now, the sum of pH and pOH is 14. And this is going to be true for any aqueous solution, no matter what. The sum of pH and pOH. What? Did somebody say something?
Sorry.
Oh, okay. I'm gonna keep going. So for any aqueous solution, pOH plus pH is always going to be 14, and the product of the concentrations of hydroxide and hydronium will always be equal to Kw, or 1 times 10 to the negative 14. Okay, so the scale that I've been using to teach acidity and basicity for a while, which has worked great, is as follows. So you've got acids and bases that come in pairs. So usually for a really great acid, the conjugate base is going to be completely hopeless as a base. So for example, you've got hydrochloric acid, very strong acid. Cl- is a very, very, very bad base to the point that it doesn't even act like a base. Now, on the other extreme, we have a really great base, like hydroxide, the hydroxide ion, and its conjugate acid, water, is a very, very, very bad acid. It's barely acidic at all. In the middle of those two, we have decent acids, which then have decent conjugate bases. And so that's the example of that is acetic acid and acetate. So if you put some acetic acid in a solution, it'll dissociate a bit, give the solution a bit of acidity, but not as much as HCl. But if you put acetate in a solution, it will accept a proton and generate a little bit of basicity in the solution. And so that'll be important later. So, okay, so notable acids and bases. I don't expect you to memorize this right now or write everything down, but the more familiar you are with these species, the better equipped you'll be to encounter them on the exam, because there really are a finite number of like common acids and bases that they can throw at you on the MCAT. And usually they'll give you some sort of clue based on like a clue to figure out what type of species it is if you don't know it. But if you've studied these species beforehand and remember which ones are weak and which ones are strong, then knowing it beforehand will make it much easier to know what you're doing in those problems. How do you recommend getting more familiar? I mean, I would say, I like, honestly, the most basic and most effective way to do it is like Quizlet it, because eventually you'll start remembering which ones are which. Some of them you might even heard of already, like nitric acid, sulfuric acid are pretty strong. There's also, is somebody's mic on? I'm getting an echo of myself. Okay, it's gone. Okay, so I would say like Quizlet is a really good way to do it. Like just do it a little bit every couple of days, like every day, 5 minutes, 10 minutes, and you'll pick it up in a week. You'll know all of these, and then you can also kind of think about like the halogens are all strong acid. The hydrohalogen acids are all strong except for hydrofluoric acid, stuff like that. So yeah, it's just a matter of drilling and practice. Okay, I got another question for passage. Okay, so usually you won't. I would say that in these types of situations, you're going to be given plenty of clues. So for example, like if there's a lot of resonance, like if it's a very resonant stabilized molecule, it's more likely that it's a better acid. If there's resonance that draws an electron pair away from a given site, it might be less basic because you're reducing electron density. So I mean, a lot of it is kind of intuiting, like looking at electron density, whether there's high electron density or low electron density for a base. And how do you know what resonance structure is the most likely? So with resonance, there's a whole set of rules that we might go over at a future topic session. So I would say essentially you kind of have to use the principles of acidity and basicity to determine that. You might also notice that some of these, like a thing that you encounter looks like one of these acids. Like if it has a carboxylic acid group, that'll tell you something about what kind of species it is. So more resonance would be stronger bases. Okay, so let's just think about it in terms of bases. Okay, so if you've got an acid, yeah. So an acid. So let's say you have an acid that loses a proton and has a negative charge. Now that conjugate base now bears a negative charge. If resonance is stabilizing that negative charge, that means the conjugate base is more stable, which means the acid is stronger. So a stronger acid will have a more stable conjugate base. A strong base will have a more stable conjugate acid. So you kind of that can kind of tell you like whether if you're comparing two species or thinking about whether it's strong or weak, a very stabilized conjugate is a clue for strength, especially when it comes to strength of an acid and stability of a conjugate base. Okay, so All right. Any other questions? Okay, hearing and seeing none, I'm going to continue. Okay, so let's talk about the common ion effect. So this is something that will definitely come up with come up on the MCAT. Yes, yes, Pranav is exactly right. Yes. All right. So, okay, common ion effect. So when you're dissolving a weak acid or a base that shares an ion or has a conjugate that with a dissolved salt that's the same as one of the ions in a dissolved salt, the effect of the acid or base is diminished. Okay, so that's a lot of words to say something that's actually easier to see than to hear. So let's say we've got a system like this. We've got acetic acid dissolving in an aqueous solution. So we establish an equilibrium. Most of the acetic acid is in its undissociated form, but we've got a bit of dissociation. And our source of acidity is the source of acidity is going to be this in green, the hydronium ion concentration. And so we've got a happy little equilibrium here, but let's say that we've now got an excess of sodium acetate showing up. Now note that, just make sure you know that it doesn't matter whether the acetate was already present or whether we're adding it after the acid, the effect is going to be the same. So based on Le Chatelier's principle, which dictates equilibrium and equilibrium changes, when there's an excess of a species on one side of the reaction, that can actually push the reaction equilibrium away into the other side. So if we so acetate is the conjugate base of acetic acid. And if we look here, if we compare this slide to this one, we now see a huge influx of we see a huge influx of acetate. So now the acetate levels are too high. So for the equilibrium, so then Le Chatelier's principle says that the reaction is going to shift to the left. So if the reverse reaction is going to accelerate, that means that we're going to consume acetate and we're going to consume hydronium ions to produce acetic acid. Now, if we do that, we're going to reduce our acidity. And so now we have our old acidity value here, but now because of that excess acetate, we've reduced the amount of dissolved H3O+, which reduces the overall dissociation of the acid, which reduces the acidity. Okay, so a couple of examples. You have NH3, a weak base, in a solution of NH4+, where a solution of NH4Cl, which releases NH4+ into solution, and NH4+ is the conjugate acid of ammonia. And then we have HCN, or hydrogen cyanide, or hydrocyanic acid. It's a weak acid, and in a solution of sodium cyanide, which contains cyanide anion, which is the conjugate base of hydrocyanic acid. Okay, any questions? Ammonia and NH4. Okay, yeah. So the definition of in a common ion effect, what's happening is you have so NH. Let me see if I can write. Can I write?
Nitij?
Yeah.
Sorry for interrupting.
No, it's okay. I asked you. Yeah, go ahead.
So for the common ion effect, when you're talking about that one, it can be like ammonium chloride is like a salt, right?
Yes.
So it's like a base in a salt solution or an acid in a salt solution.
Well, basically the overall point is that the salt contains the conjugate of the weak acid or base that's also in solution. So in the first example, NH3 is the weak base, and so its conjugate acid NH4+ is part of the salt.
Gotcha.
That reduces the amount that NH3 is able to act as a base, because it imbalances the equilibrium, which forces more NH3 to be formed instead of acting as a base. And then in the other example, we've got a weak acid that whose conjugate base, cyanide anion, is present in the salt. And the same thing happens, but it's just instead of a weak base and a conjugate acid, it's a weak acid and a conjugate base.
So basically just the base, so it's like we can assume like it's going forward. So we have a base that will react with some salt that would form, it's going to form like a base chloride or an acid, no, a base salt and an acid salt. So it's just the conjugate part of it.
Well, so it's not like, so there's two separate sources. So we look back at the acetate example. You see how we have our acid equilibrium, right?
Yeah.
Then we throw in our salt, and that forces the equilibrium to go to the left.
Yeah. So my question over here is when I look at this, it looks like Le Chatelier's principle. Is it something like that? Is it related?
Yeah, it is Le Chatelier's principle. Yeah.
Okay, just wanted to confirm that one.
Yeah. So the common ion effect is a consequence of Le Chatelier's principle, where a weak base or weak acid is less able to be basic or acidic when its conjugate is present via a salt.
So
like
when we add
conjugate.
Sorry for asking so many questions.
It's
so
okay.
when we a base or a conjugate base or a conjugate acid to the product, it will reverse it backwards. So when we add something to the product, that means it's going backwards. So that's
yes. Yes.
Okay, thank you so much.
Mm-hmm. Okay. To everybody else, are we good with that? We're good with the common ion effect? Okay. Excellent. So, and if you realize you have a question later about something I did before, you can still mention it. I might finish the. Oh, thanks. All right. So titrations. So our first type of titration is with a strong acid being titrated by a strong base. And I would guess that almost all of us have seen this before. So at complete neutralization, the only species that are remaining are Na plus, Cl minus, and H2O, since we're reacting HCl and NaOH. And none of those species are acidic or basic. And just to clarify, the conjugates in this case, conjugate base of HCl is Cl minus, very bad base. Conjugate acid of OH minus is H2O, very bad acid. So that because there's no acidic or basic species in solution, our equivalence point pH is going to be 7 or neutral. So that's pretty straightforward. We've got our standard, like not really changing in slope initially, and then it shoots up, and then it establishes itself after the equivalence point at that very basic pH. So now let's look at a weak acid and a strong base. So for example, acetic acid, CH3COOH, and NaOH, sodium hydroxide. At complete neutralization, the remaining species are going to be Na plus, which doesn't do anything, H2O, which is also neutral, and acetate, CH3COO minus, which is the conjugate base of acetic acid. But if you remember that table of the acid scale, acid and base, like conjugate scale, acetic acid is a decent acid, which means that acetate, its conjugate, is a decent base. And since acetate is basic, and there's nothing else, everything else in the solution is neutral, the equivalence point pH is going to be basic or above 7. And one important thing to note here is that for a weak acid strong base titration, the half equivalence point, where half of the acid molecules have been neutralized by base, but half of them are still remaining as acid, that's where the pH of the system is equal to the pKa of the weak acid. And we'll come back to that momentarily. Okay, any questions about titration? Yes. Okay, so the half equivalence point is where, so let's say you've got a mole of acetic acid in your bucket that you're doing your reaction in. When half a mole of that acetic acid has been converted to acetate, that's the half equivalence point. A weak base and a strong acid pH is less than 7. Yes, that's correct, because then the weak base has a decent conjugate acid, which then lowers the pH below 7. So it works both ways. Does that make sense? And we'll get to why the pH equals the pK at the half equivalence point in a minute. Any questions? Okay. Okay, so we'll continue on to buffers. So what makes a good buffer? There are 3 elements of what makes a good buffer. First is a weak acid or a base, so like acetic acid or ammonia, and its conjugate base. So it's kind of a pairing. You have a weak acid and its conjugate base, or a weak base and its conjugate acid. And a ratio of no greater than 10 to 1 in either direction of those 2 species. So there can be no more than 10 times as much acid as base, and no more than 10 times, let me rephrase that. No more than 10 times more acid than base, and no more than 10 times more base than acid. If you go any higher than that, you're then outside of the effective buffering zone. So some examples are NH3 and NH4 plus, CH3COH acetic acid, and CH3COO minus acetate, H3PO4 phosphoric acid, and H2PO4 minus dihydrogen phosphate. Okay, so calculating the pH of a buffer. So we can use the Henderson-Hasselbalch equation to calculate the pH of a buffered solution, which is pH equals pKa plus the log of the quotient of the basic species over the acidic species. And this only works if the acidic and basic species are conjugate. If you have, like, I don't know, acetate and ammonia, that's not going to work. The acidic and basic species have to be conjugate. Where's the buffer region? Okay, yeah, so the buffer region, we'll be getting to that in just a minute. Okay, so remember how we said that that the ratio of basic to acidic or acidic to basic can't be more than 10 to 1 in either direction? That's because those 2 extremes make the log term either +1, since log of 10 is 1, or -1, since log of 1/10 is -1. So the upper bound is our pKa +1, where and up until that point above pKa, the base, there's more base than acid, and the lower bound is pKa -1, where between that point and pKa, the acid outnumbers the base. And when the 2 are equal, when acid and base concentrations are equal, the log term becomes 0 because it's the log of 1, and pH equals pKa. So our buffer zone is going to be centered on our pKa value with a range of plus or minus 1 pH point. Okay, and we go too high above that or below that, we are outside the buffer zone, and so it's no longer as effective. So let's return to that acetic acid titration. So we've got our equivalence point and our half equivalence point. And remember, that's where half the acetic acid molecules have been converted to acetate. So we started out with a mole of acetic acid. Now half a mole of that is acetate. But that leaves half a mole as acetic acid, which means that we now have 0.5 moles of, or we assume we have a liter of solution of 0.5 molar acetic acid and 0.5 molar acetate. Now, if we go back to this equation, 0.5 molar of both basic and acidic species means that we have equal quantities, and that makes the log term 0, which means that pH is equal to pKa at this half equivalence point. So the buffer region is actually pretty easily identifiable on this titration curve, and it is centered at the half equivalence point where pH equals pKa, and plus or minus 1 pH point. Does this mean the buffer zone is in the Zwitterion? The Zwitterion region only really applies to amino acids, and it's going to be so. And so you'll often find that amino acids are going to have multiple pKa's because they have different groups. So like starting from if you're titrating an amino acid, you're going to start out. You're going to first have the pKa of the carboxylic acid group. Then you're going to have the pKa of, depending on what the side chain is, you might have a side chain pKa, and then you'll also have the amino group pKa. And so the Zwitterionic point doesn't really apply in cases like where you have like things like acetic acid or like acids that only have one acidic group. We'll probably have a topic session on amino acids, that's probably a good idea, where we'll go over Zwitterions and amino acid titration. So it's a good point to bring up. Okay, so questions. So we covered this is kind of a connection of what we've been talking about so far. So I want to stop and see if anybody has any questions. Any of you want to go back to a previous slide or go over anything from the last few slides? Okay. Starting from here.
Yes.
Okay. Okay, so let's see. So I'm going to answer. Okay, so the buffer region is centered at the half equivalence point, and the half equivalence point is where conjugate base and acid are equivalent in concentration. Do you have any specific question about the last 3 slides?
I guess like what should we expect like as a question on MCAT, kind of connecting this equation?
Oh, I have some practice questions. I don't know if I think I do have one on Henderson-Hasselbalch. So yeah, we can go over that. But it's definitely really good to know this equation and be able to use it. And there's Henderson-Hasselbalch practice questions floating around everywhere. So it's just, you shouldn't have any trouble finding some practice for this stuff. Okay. I might be pronouncing this wrong. Tuyet, you said, can I go over the last 3 slides? I don't know if you're the one I just talked to, or I can't see when I'm sharing my screen.
Yeah.
For
the titration curve,
yeah.
Can you go over that again?
Yeah, sure.
I just I'm having a hard time understanding it conceptually.
Okay. So so let's start from the basics. So the equivalence point, it's where the acid and base are fully neutralized. Yeah. So so then the half equivalence point is where half of the acid molecules are neutralized. So at the full equivalence point, all the acid molecules are converted to conjugate base. At the half equivalence point, only half of those molecules are converted. And so that means if we started out with all acid or almost all acid, and then we converted half of it to conjugate base, now we have equal amounts of conjugate base and acid. That means that pH equals pKa, which is the half equivalence point and the center of the buffer region.
Okay. And so for a good buffer, would we want it to be at the equivalence point?
A good buffer So the buffering region is in this, in like the green box. So so the range of pHs where this would be a good buffer for is about 3 to 5, if the half equivalence point is at pH 4, which is the pKa of 4. So this acid base buffer system, or this particular acid and conjugate base, would be for this range of pHs. Like it wouldn't be a good buffer region for like pH 8. You'd want to use something else for a pH 8 buffer, because the pKa is 4, which is not near 8.
Okay, thank you.
Yeah. Yes, exactly. That's exactly what the half equivalence point is. So you might get a question that is going to be like, oh, given this list of 15 acids and their pKa's, which one would be the best to use in a buffer at pH 4? And you want to pick the one whose pKa is the closest to 4, because it's most likely that 4 will be in that buffer region. Does that make sense? Choosing an acid for a buffer is something that you definitely have a chance of getting. Okay, so this is a magic trick that I found on Reddit of how to quickly calculate pH from a hydronium ion concentration, because calculators aren't allowed. So let's say that we're given an hydronium ion or proton concentration of 2 × 10⁻⁴ molar. So what you do is, this is an approximation, obviously, but you take the 4, which is the exponent, or -4 is the exponent. You take the 4 and you subtract 0. And then the base of that, or 2, and you get 3.8. And the actual pH is 3.7. So you can use that as a pretty easy way to shorthand and go back and forth, or at least from hydrogen ion concentrations to pH. Yeah, that was my reaction too. So it's pretty helpful. I used it myself. Okay. Okay. So given a solution, and you're given the, okay, that's good. Log tricks is really important. So yeah, but in this case, you'd given a hydronium ion concentration, you've got 2 × 10⁻⁴. You take the -4, so you take the 4, and then you subtract 0.2, since 2 is the base of that exponential term. 4 minus 0.2 is 3.8. That's your estimated pH, which is very close to 3.7, the actual pH if you use a calculator. Okay, so practice. All right, so what I'm going to do is I'm going to leave this up for a little bit, and then we can talk about it. So I'm going to give you guys a couple minutes to figure this one out, and you can confer in the chat. You can put your answers in the chat. I'm not grading you. No one else is grading you, so it's okay if you're wrong. So yeah, go for it. Oh, they're the HClO and HOCl are the same thing. They're just, yeah, it's just convention.
Nitij, do you want us to write the explanation, or are you good with just the
I mean, if anybody wants to volunteer an explanation, go for it. I mean, you're like, so far everybody is right. So who wants to give us the explanation for this one? Okay, good. I'll take it. Okay, so yeah, Le Chatelier's principle. If you are going to flood the system with extra hypochlorite ions, you're going to increase the reverse reaction rate, and that will produce more HClO. Now, what will happen to the pH of the solution? I'm asking that as an extra question.
Increase?
Say that again?
Increase?
Yes, it would increase. Why?
Because we're having more HClO. So when we have more of the HClO, it's gonna, since it's an acid, the pH is gonna increase. Since
Well,
more of it is being produced.
You're okay. So let me explain it else, and let's see whether we're saying the same thing. So
Okay.
if you're producing more HClO, you're consuming hydronium ions, and if you're consuming hydronium ions, you're increasing the pH because the solution is becoming less acidic. Is that what you were saying?
Yep.
Okay, good. All right, let's continue to the next one. Could you
Oh, if that equation was like only like didn't have that equilibrium arrow and it was only to the right, and if we increased hypochlorite ions, then the equation would actually be the concentration of HClO would be decreasing, right?
Can you say that again? If it was a single arrow, there's no equilibrium to speak of, so it doesn't really do anything.
Nitij?
Yeah.
But I don't think there's gonna be a single arrow, because a single arrow is like for strong acids and strong bases, right?
Exactly. Yeah. So for example, if you had HCl and you threw in a bunch of Cl, it's not good. The HCl doesn't care, so it's going to dissociate just as much. There's no equilibrium there.
Okay, so this is a weak acid, so there is equilibrium.
Exactly. Yeah.
Okay, thank you.
Yep. Hypochlorite versus okay. So hypochlorite. So I'm gonna type it in here. Hypochlorite, chlorite, chlorate, and perchlorate. So hypochlorite is ClO. Chlorite is ClO2. Chlorate is ClO3. Perchlorate is ClO4. So one way that I use to remember it is hypochlorite is at the very bottom. That's one oxygen. Chlorite is right next to it, therefore it must be the 2 oxygen one. Perchlorate is at the very top, so it's got 4 oxygens, and chlorate is right below it, which means it has 3. I don't know if that helps.
Nitij?
Yeah.
Sorry for asking so many questions.
No, it's okay. You can ask questions.
Just to confirm,
yeah.
all of these, the ones you listed, have minus charge because they don't have hydrogen, right?
That's right. They all have a single negative charge, -1.
Okay, thanks so much.
Yeah. Does that help? Okay, good. Okay, so let's do another one. Try to do it without a calculator, because you don't really need it. Okay. If you guys need more time. All right, I'm seeing some B's. Any agreement, any disagreement from anybody else? Okay, another B. Okay, one of y'all who answered B, why? Why did you choose B? You're correct. Why did you choose B?
I think it's because of the Henderson-Hasselbalch equation.
Yes. So how did you use the Henderson-Hasselbalch equation?
So basically, we convert K into PK. We convert, no, we don't convert AK, but we just do 10 the power of the PH minus PK, right? No, PH plus PK. So I said minus PK because it's -4. So PK is going to be -4. And when you take it to the other side, it's going to be +4. So yeah.
Good. Yes, that's exactly how you do it. So this is an example of something you might get at a as an MCAT question about where you have to use the Henderson-Hasselbalch equation. And you guys nailed it. Good job.
Wait, I'm sorry. Can you work that out because I didn't really understand.
Okay. Yeah, I can. Let me pull out a whiteboard here. Okay. Let me see if I can do this. Okay. So, can y'all see this?
Yes.
Yes.
Okay,
Yeah.
equals 1 times 10 to the negative 4. And then pH equals 6. Concentration of HA equals 10 to the negative 8 molar. Okay, so if we plug this in, so we have our Henderson-Hasselbalch equation. Let's say that so we first convert our Ka into pKa. And so that's going to be 4. And so we have 6, which is our pH, equals pKa of 4 plus log of A minus over 10 to the negative 8. And so basically what we're going to see is that log A minus equals, what's the best way to do this? You have log A minus over 10 to the negative 8 equals 2, which means that it's been a while since I've done logs. Basically, the point is that A is going to be 100 times HA because if the log of concentration of HA over the concentration of the log of the concentration of A minus over the concentration of HA is 2, there's 100 times more A minus than HA. Does that make sense?
Yes.
Still a little confused on that explanation.
Okay, let me back up. So until when did it make sense?
It made sense when you would subtract 4 from the 6 to try to solve for the concentration of A minus.
Yeah. Okay. So.
But how can we do this mental math on the MCAT without the calculator?
Okay. There's a good explanation in the chat.
To cancel out the log, you do 10 to the power of. So 10 to the power of 2 is equal to A.
Yeah. 10 to the power of 2
is equal to A. over,
A over
10.
10 to the 8. 10 to the negative
That's how you solve it.
Yes.
10 to the 2.
So you just say 10 to the power
Oh,
of.
got it. Okay, yeah.
There we go.
Okay,
That was
thank you.
the missing step. So then you do 10 to the 8, 10 to the negative 8, and 10 to the 2, which is 10 to the negative 6, which is your concentration, which is your answer. Yes, and the rationale that that Pranav is providing in the chat is really useful too. So if you have more base, it must be higher than pKa. If you have more acid, that must be lower than pKa. And a difference of 2 is a 100-fold difference. And a difference of 1 is a 10-fold difference, etc. So you can, the more you practice that, the more comfortable you'll get with it too. Okay, are we good with that? Okay, let's keep going. Okay. Oh, okay, you might have already seen the answer on that one, but you still have to justify it. So go ahead and put the answer / explanation in the chat once you've got one. Okay, we've got 1D. Any agreements or disagreements? Okay, we've got one person saying C, others C. Okay, so it is C, because neither acids nor bases are going to release hydrogen gas. Right, exactly. So a Bronsted, so when you lose a proton, donate a proton, or accept an electron pair, you they tend to, not always, but usually get a net negative charge. So yeah, that the letter C is the answer to that one. Okay, this actually, somebody brought this up at near the beginning of the session. Who was it that brought, when we're talking about acetic acid and sodium hydroxide, somebody brought up ammonia and HCl. We briefly mentioned that. Okay, so I'm seeing some B answers and some C answers. So anybody who's answered yet, go ahead and, or anybody who hasn't answered yet, why are you saying either B or C? I'm seeing a couple justifications for B. people who said C, what makes you think that? Yes. Okay. So, all right. So C is the correct answer because once at the neutralization point, you have. Okay. So it is an equal mixture, stoichiometric mixture. So it's not because there's more H plus ions. There's equal amounts of HCl and ammonia, but at the neutralization point, NH4 plus is the dominant species that remains, and NH4 plus is a weak acid. And so this is where weak doesn't really mean, it means weak-ish. So remember we had like strong, like great acids, really bad acids, and decent acids. So, and the same thing with bases. So NH3 is what I would call a decent base. Yes, if you email us and want the recording, we will get it to you. Yeah, okay, so does that make sense to everybody?
Sorry, I still didn't really get it.
Okay, so let's go back to, let's see how I can go back to slide here. Okay, so remember this, when we have our weak acid and strong base, when we're at the neutralization point, we've got the only things in solution are going to be Na plus, water, and acetate.
Mm-hmm.
And acetic acid is a weak acid. It's so I would call it decent acid. Because it's not so weak that it's useless, but it's not that strong either. So it's kind of it's like weak-ish. So that means that acetate, its conjugate, is a weak or decent base.
Okay.
And so if acetate is the only pH modifying species in solution and it's a base, it's going to raise the equivalence point pH a little bit over 7. So like 8 or 9 or something like that, depending on concentration.
Mm-hmm.
Now we go back to this question, it's pretty much just flipping it around. Now you have a weak base being titrated by a strong acid. Now at the equivalence point, all you have is Cl minus, which does nothing, water, which does nothing, which I assume is part of the solution, and you have NH4 plus. NH4 plus is a weak or decent-ish acid because ammonia was a weak base. Ammonium, NH4 plus, is a weak acid, and so since that's the only pH modifying species in solution at the equivalence point, the pH of the solution will be less than 7.
Nitij?
Yeah.
Okay.
Sorry.
Okay, got it. Thank you.
Yeah, go for it.
I had a quick question. I was a bit confused on this question because it says that the stoichiometric mixture is neutralized.
Yeah, so the neutralization just means that the acid and the base have neutralized each other. That doesn't mean that it's a neutral solution. That's where it can get kind of confusing. Because
Okay.
the acid and the base have neutralized each other. It's just that the remaining species is slightly acidic. So
okay. So basically, we're just considering the acid and base instead of the whole solution.
Right. Yeah. So that might have been a little bit unclear, but yeah, I think it's basically that the acid and base have reacted fully and in a 1-to-1 ratio.
Okay. Thank you so much.
All right. Any other questions? I think we have 1, maybe 2 left.
How do we know if an acid overrides a basic?
What do you mean?
So if a basic and acid is mixed together, how do we know which one is stronger?
Well, usually it'll tell you, or it's like a common strong species like HCl or HNO3 or stuff like that. That's one of the reasons why I think it's helpful to like memorize some of those common ones, because then you can, in case they ever try like throw one of these at you, you don't have to like spend time trying to figure out what type it is. You can just remember. Yeah, I would personally recommend knowing the strong and the weak ones, especially the ones from that list. I pretty much thought of all the ones that I've seen so far, and it's not that much effort, but it can be really helpful, which is why I think that it's worth doing. Okay, and Kwan is going to tell us in a future session how you memorize using the periodic table. Okay, I look forward to that. All right, any other questions about this one? Okay. All right, let's take a look at this one. No, you don't. The periodic table will be given to you. Like there'll be a little button you can press to pull up the periodic table on the MCAT. So do not memorize the periodic table. It's not going to be useful. It's not even useful in general because you can just look it up anywhere. So don't. Oh, strong. Oh, yes, yeah. So I would say, I mean, know the trends. The trends are not going to be on the table, so you have to remember the trends. But yes, he clarified that. Okay, right, go ahead and I'll give you another minute to do this problem. Okay. So I'm seeing a couple people saying D. Any agreement or disagreement from people? Okay, I'm seeing a B. Okay, so we can go over it. I'm going to try to use the whiteboard again. Okay, so let's look at our values here. We've got Ka equals 10 to the -1. And then we've got concentration of HA equals 0.1 molar. And then you have concentration of A minus equals 10 molar. So we can first do what we did before and convert that Ka into a pKa of 1. Okay, now we put in our equation, our Henderson-Hasselbalch equation. pH equals pKa plus log of 10 molar over 0.1 molar. This is equal to log of 100, which is equal to 2. Therefore, our answer is pH equals 1 plus 2, which is equal to 3.
Will the MCAT give us questions like this where we have to figure out log of 100, log of 1,000?
Log of 100, log of 1,000, you should be able to do without. I'm sorry. You should practice doing that without a calculator. Don't feel silly. It's okay. That's why we're here. We're here to figure out how to do this stuff together.
So we should memorize logs of 100 and 1,000.
Yeah, wouldn't hurt. Yeah, and Kwan said he'll be doing log tricks. So, but it would be helpful to know like log of 1,000 is 3, log of 1,000,000 is 6, etc. Yeah, I'm not gonna step on Kwan's toes here. He will bedazzle you with logarithms. So let's see. I think, okay, yeah, okay. So before we talk about some housekeeping stuff, are there any questions overall about content? Anything you want me to go back to? Any broad or specific questions about this subject?
So when like we're given like ammonium, like NH3, and it's like in solution either like a strong acid, we'll have to know its conjugate base or conjugate acid.
Well, can you repeat your question?
I guess it's been so long since I've taken Gen Chem and OChem. Sure. It's been like more than 5 years. I'm sorry.
Okay. That's okay.
I'm just like confused because like in the some of the questions were given like ammonium, like NH3. How do we know that it'll have to dissociate to NH4 plus?
Well, I would say, like if NH3 is a weak base, right? And that's one of the common ones.
Mm-hmm.
So in this case, it's going to donate an electron pair or accept a proton, which makes it NH4 plus. So that's what it. So when NH3 acts as a base, it turns into NH4 plus.
Oh, in a buffer system.
In a buffer system, I'm not sure I understand your question. So I mean, NH3 is a weak base, which means that if you combine it with a solution that has NH4 plus in it, you can make a buffer solution.
Okay. So when NH3, which is a weak base, is titrated with a strong acid, how do we know like that titration causes NH3 to becoming NH4 plus?
Well, if it's reacting with an acid, it's a base, it's going to accept a proton.
Oh, okay. So NH4 is actually an acid.
NH4 plus is the conjugate acid of NH3.
Okay. So it's a weak conjugate acid?
Yes. Ammonia is a weak base, ammonium ion. So ammonia is NH3, ammonium is NH4 plus, and they're both, one is a weak base, one is a weak acid.
Okay, got it. Thank you. Sorry.
Mm-hmm. Okay, general question. What do you think about UWorld practice material? I mean, we can, the other odds can talk in here. I would say I personally love UWorld. I think that between UWorld and AAMC, UWorld and AAMC, those two are the number one. Well, number one is AAMC, number two is UWorld, I would say, as far as quality. UWorld pretty much covers every single possible thing you could ever encounter on the MCAT, and it's really great for practice. It's really great for like figuring out how good your breadth of content is. And UWorld isn't I mean, Kaplan and Princeton Review, they're trying to just scare you by like throwing a bunch of crap at you that you don't actually have to know. And UWorld doesn't do that. UWorld just increases the difficulty without increasing like the depth of the content. So it challenges you without making you feel terrible. So I love it, and I would 100% recommend it. And how long the session is going to be usually? We're kind of working that out. We've usually gone around an hour, though I see that we've gone over that today. Usually we have 30 minutes to 45 minutes of content, and then extra time for questions, but I've kind of had questions in between. So yeah, exam crackers. Yeah, listen to Quan. I don't know much about exam crackers. But yeah, I would just say in general, some of the third-party stuff, they will go. Yeah. Yeah. Yeah, I would say UWorld is really good for like once you're kind of like partway through once you're like kind of through your content and you want to try flexing your muscle a little bit. UWorld is good at doing that. I used UWorld to identify all the gaps in my content. So if I went through UWorld, I was like, oh, I didn't know that. I'm going to go study that. And I just did that for the entire UWorld set. And if you do that, if you give yourself enough time to go through everything you don't know, there'll eventually be very little that you don't know. And if you keep track of all your mistakes and go over them and systematically be like, okay, I got that wrong. Here's why. Here's what I got it wrong. Here's how I'm going to fix it. And then you do that for all of your mistakes over a few months, you're going to do much, much better over time. Somebody asked, how long is the tutorial going to last in long-term plan? What do you mean?
I mean, is it going to stay like until like next year or something?
Is it going to what?
Is it going to stay? Are you guys going to continue this for a short term, or are you guys going to continue until like next year?
Continue the topic sessions and stuff?
Yeah, the topic sessions. Yeah,
oh, yeah. I mean, we don't have an end date planned. We're just going to keep going.
Okay. Thank you so much.
Yeah.
I know this question, like, we may, like, all of us may not, like, completely can predict the future on it.
Okay.
But I know that the AAMC only shortened the exam to like 5 hours, 6 hours this year because of COVID. And I know that the exams will go back to normal next year.
I think they have gone back to normal. I don't know for sure.
Yeah, I think they have already.
I think it only lasted until the end of last month.
Yeah.
So
because of that conversion, do you think it's gonna go back to like being hard again because the shortened exam was probably easier?
I don't know if the shortened exam was easier because they shortened the time too. And I think I heard a rumor that they threw out like some of the experimental questions that don't actually count. If a lot of people do bad on them, then they don't count them. I wouldn't worry too much about yeah, they removed the dummy questions, meaning like the ones that are like, let's see if they all get destroyed by this question or not. I would say don't worry about it. I don't think you need to really change what you're doing because yeah, like Quan says, you're being measured based on everybody else too. So if everybody else gets screwed by something, chances are like if you get screwed by something and everybody else does, it's not going to hurt you. So I wouldn't worry about the change in the MCAT because it's yeah.
So I got like a really low diagnostic score that I took over the weekend. It was like 50th percentile diagnostic score, and my planned exam is next year in May. Do you have any tips on improving?
I think Sim brought this up earlier, and I did too. Like aggressive identification of your mistakes. So like you just keep track of like every single thing you get wrong on your practice materials. And as you go through your content, every single thing you see that you don't know, you just hit that. And then you run and do it again. You might get it right. You might get it wrong. And then if you eventually just target all of your, like you just target your review at the stuff that you're not good at or don't know, then that'll be a really good way to improve.
Okay.
And we'll probably have some strategy sessions too coming out. What were you going to say?
I'm currently in the LTS program, but it's like very different than like just Kaplan content review, and I'm also working full time, so it's like really hard.
Yeah, it's not easy when you're doing that, like when you've got other commitments. I would say I think time is the number one thing you can do. Is the number one thing you can have. And so giving yourself up to 6 months is good. Consistency is better than intensity, and that's what I found from personal experience and from talking to other people.
Okay. So do you think the LT exams are easier than the actual MCAT?
I don't have experience with it. Pranav, you want to chime in over voice?
Yeah, I've taken them.
Or anybody else?
Had like a 10-point difference between my practice test and the real test, so don't be discouraged. I thought they were a lot harder and they test more on the details. So trust your AMC test when you taking them.
And by the way, AMC actually has 4
Thank you.
practice exams. You can buy 3 as part of the online bundle, and then the 4th one you have to buy separately.
Mhm.
Yeah, third-party sources are only good for practice, except UWorld, but there's no exams on UWorld anyway, so you can't really use that as an exam anyway. But the UWorld is the only third party that I personally trust for content and not wanting to screw you. So, yeah.
Thank you so much.
Yeah, you're welcome. I got the bundle this several months ago, and I took the exam a couple months ago. I had to buy the 4th one separately. So unless they've changed that, and AMC isn't going to pass up a chance to take more money. So I think it's still going to be like that.
Nitij, thank you so much for all your help.
Yeah, you're welcome.
Thank you so much, Sim.
So just last housekeeping thing. Sim, do you want to chime in about this?
Yeah, sure. So we have a GoFundMe set up. So we're all volunteers, so we're not getting paid to do this, but we do need some funds to cover our website and advertising and other costs. So if you guys can help out with donating so we can continue these future sessions and help out more people and hopefully get you all guys through great MCAT scores. So that would really help us out a lot. That's basically all I have to say, but here's the link. Oh, I think I sent that privately. I think someone mentioned going over all the components and topics in the MCAT exam.
What?
I think there's a question in the chat.
Can we do a session going over all the components what do you mean? Do you mean like because that's a lot, so I'm like, what specifically are you looking for with that?
Just like a simple bullet point list or something like that, like a checklist for us so we can know which topics we need to review.
I can actually do you one better. This website right here has every single thing every single subtopic that can show up on the exam. I've used it personally. I use it to make this content session. So yeah,
Okay.
there's also the AMC official site. Although
yeah, if you
there's
guys,
that. It's the AMC is it's kind of extra technical and verbose. Although it is good to look at because it also is pretty detailed. So I would say use the website that I sent and this AMC document that was attached as well. Yeah.
Do you think we'll like be able to have like a cars like jam sesh sometime?
Yes. I am sure we will. I think we've had one so far that Sim has led, and I'm sure there'll be more in the
yeah,
near.
there's actually one tomorrow. So come through to that. And we just do a bunch of car strategies and practice. So if you need more help on that, come through and then we'll talk about it there.
Yeah. Also, Jack Weston for cars, also good daily practice. Do I mind sharing my MCAT score? I don't. I do not mind. I'm going to put it right here in the chat. I don't really care that much. I studied for about 4 or 5 months. And I really think it's hugely a function of like, because it's all about studying smart for it, because if you do that, then and I mean I also took it like right after I took biochem and physics, so there's also that. But use that to remind yourself that the power of practice over multiple months. So that's the lesson you should take from that. Self-study full. I studied part-time, but I took like a reduced course load for a semester, and then dedicated a few hours a day to MCAT. And then we had quarantine, and I got even more time to study for it. So did I work? I did not. I normally had a part-time job as a TA, but I stopped that for spring semester so I could put in extra time on the MCAT. I also stopped. I was also doing research until then. Then I kind of dipped out of that for a semester also to focus on the MCAT. Okay, so thanks. All right, so if there are any other last call for questions, and if you think of other questions, you can email us at mcat101questions@gmail.com. Yeah, if there's nothing else, anything else on your end, Sim, you want to mention?
No, I think I'm all good. We have upcoming topic sessions, so look out for those.